The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Right, okay, so I guess we ought to start. We seem to be a bit depleted today.
All right.
And anyway, right, so today, last time we spoke about 4F imaging system and a bit about spatial filtering, and I guess we're going to do quite a lot more on that today, really. So, I mean, this is really the most basic part of Fourier optics, really, I think, and so you need to get lots of practice at seeing how it all works, so that you can, until it comes sort of second nature, really. So this is what we said last time. We went through this slide last time, showing the significance of the point spread function of a low-pass filter. The idea is that if you put in a point object, i.e. you put in an opaque screen with a small hole in, illuminate that with light, this is going to then give a spherical wave, and then this lens is going to collimate that spherical wave to make a plane wave. And in this back focal plane of that lens, you will get a nice smooth variation here, or no variation, uniform intensity, uniform amplitude, which is basically the Fourier transform of this delta function. Fourier transform of a delta function is a constant, isn't it? And then this light then goes through a pupil mask. The plane wave after the mask then gets to this second lens, and the plane wave is then focused down and produces a focus spot at some image plane, right? So that's how it all works. So now what do you actually see here? What's the image of a single point object? What you see is the Fourier transform of this pupil mask, because again, this is also producing a Fourier transform, right? So the point spread function, what's called the amplitude point spread function, is just the Fourier transform of this pupil mask. And we sometimes talk about an intensity point spread function, which is actually the modulus square of that, the intensity in that image of a point object. Okay, so, and this is reminding you where you might have come across this sort of concept before. This is like we spoke in the last lecture about if in electronics you might think of an electronic system like an amplifier or something as a sort of black box. You put in a signal and you get out a signal, and you can characterize that black box by what's called the impulse response, which is the response that it would give to a sharp spike going in. All right, so ideally you'd expect you'd want a sharp spike to come out as well, but in practice you don't get that. You get some sort of broader function because of the imperfections of the transfer system. Okay, so this is our point spread function, and it's denoted little h of x dash y dash. This is the x dash y dash plane. I guess this terminology, little h, seems to be pretty universal. Goodman, I think, uses that and other places, right? So, okay, and this is just now describing again how you calculate this 4F system. We notice everywhere that we notice that the input transparency of a delta function gives 1 here. You multiply by the pupil mask, and then you do another Fourier transform to find the image. Right, so that's... yeah, I ought to say something a bit more about the scaling of this. Yeah, so you've got, of course, the output point spread function is a function of x dashed. But of course, when you do a Fourier transform of something, it's going to be a function of frequency, not of distance, isn't it? So really, this h here, h of x dashed, we get by doing the Fourier transform of this, and then transforming the coordinates, scaling the coordinates in order to get it into the coordinates x dashed. Okay, so, and then last time we also, I'll go through this very quickly, what we said last time. If you've got a low-pass filter, i.e. in 1D, like a slit pupil, then the pupil mask is a rect function, and so if we're trying to calculate the image of a point object again, the field when it gets to this pupil plane is just a constant, and so after it's gone through the aperture, it will have this sort of amplitude variation, and then right. So this is what this is showing. On the positive side, it's what's on the negative side, which is just 1 times this, which is this, and then if you then Fourier transform that, you find that the point spread function is going to be the Fourier transform of this, which is just a sinc. And then the point spread function is the Fourier transform of this, and then this is doing the scaling of the coordinates and getting into the right sort of size. I'm not going to go through that. We went through it last time, but hopefully we're going to. Yeah, here we are, and there's the sinc. Right, so this is the amplitude point spread function, or just normally called point spread function. Note that it goes negative. This is 0 here, so note that it goes negative, right? So you've got to convolve that with your object to find the image of some arbitrary object, which we'll carry on to talk about in a minute. But this was just another example of a phase filter. And the Fourier transform of that, but I don't think there's any point going through that again. We'll just carry on now with where we've got up to, which was to do with shift invariance of the 4F system. Now what we've looked at, is if we've got a point object that we get from this hole in a screen, we get an image which is this amplitude point spread function. The amplitude here would be this Fourier transform of this pupil mask. I just mentioned there is this constant. This is the point spread function. It's the Fourier transform of this pupil mask, but there's this constant out the front, and this constant out the front is written like this. You can see that it's made up of 2 parts. First of all, this phase part. This just comes about because of the distance the wave has travelled through the optical system, right? So if it starts off with 0 phase here, it's going to come up with some particular finite phase when it travels all this distance through the system. And then the other bit is this F2 over F1, which is a scaling factor, the ratio of the focal lengths. Basically, you need that to satisfy conservation of energy, right? So you can imagine that as the point spread function gets broader, then it has to also get lower, because it has to contain the right amount of energy equal to the energy going into the system. So when you if you work out the intensity of this image of a point, this would be F2 over F1 squared, which is the ratio of the heights, the maximum intensities of the center of that image of a point. Right, now, so what we're carrying on to look at now is what happens if we displace our point object. We move this delta function sideways, and then let's look first of all at just the physical situation of what's happening. This produces a spherical wave, and then when it goes through the lens, you can see that it's going to produce, again, it's going to be collimated into a plane wave. But now this plane wave is not actually moving horizontally, but is moving at an angle. And this comes about because when you Fourier transform this, you will get some exponential phase factor, right, which actually represents a wave which is moving at an angle. And then when this inclined plane wave goes through the pupil mask, of course, its angle doesn't change anymore. So it's still moving at the same angle here. And then again, it's collimated and produces an image. The image, what we find, is the same as it was before. The amplitude is exactly the same as it was before, but it's shifted. So this is what we found before when we looked at the image. You got this, you remember, this inverted magnified image. The inversion means that it's the opposite side of the axis. The scaling is this f2 over f1, which comes about from the fact that the focal lengths are not equal. But the important thing to notice is that apart from this shift, this function is the same as the function was before. So what that means is that this is what's called shift invariant. It means that the image of a point is independent of where the point is, right? So that's a very important property, which simplifies things tremendously. Yeah, and here's a note just to say that that is the lateral magnification of this system as we described before. Okay, so now we this is just showing this diagram again of these are not meant as a sort of rays. These are just sort of showing regions where the light is as it goes through. But we've got this amplitude here, which is Fourier transformed by a lens, and then goes through a mask, Fourier transformed again, field. Yeah, so what this slide is trying to show is the significance of the point spread function. Some arbitrary objects, we can think of an arbitrary object, G of t, an arbitrary transparency. You can think of, you're illuminating that with some field. So what actually you get after the transparency is the product of those two. So it's the G in that I really meant to talk about. The G in you can think of as being made up of lots of delta functions. Any arbitrary function, you can divide it up into lots of delta functions where the strength of each of them corresponds to the strength of that function at that point. Right? So this is what this expression here is writing down. So the G in is written as, you can write it as an integral over delta functions with the strength given by the function. Each of those delta functions is going to propagate through this system and produce a point spread function, exactly like we described before. And then the image of the total object is going to be the sum of the images of all these delta functions. So all of these delta functions produce point spread functions. So you integrate over those point spread functions with the relative strengths that you need from here, and you'll get the final image. Yeah, you can see that this is a bit like Huygens' principle, that you're breaking up this wavefront into lots of components that are all represented as delta functions. Okay, so yeah, so therefore what we get out is going to be this integral. Each of these delta functions is going to produce an image given by this point spread function. The point spread function is shifted a distance which depends on the original distance, but is scaled according to this factor we just mentioned earlier. And the strength of that component is given by this value g in at this point, as we said there. So our final expression says that the output amplitude convolved with the point spread function, right? So it's this expression you can see is exactly the same as an ordinary convolution expression, except but you can see it's like okay, yeah, so because of this scaling, we can, and also the inversion as well, we sometimes express things in terms of a reduced optical output coordinate. So we think of the output coordinate as being measured to get rid of the sign, and also scaled to get rid of the scaling factor. And if we do it in terms of these reduced quantities, then you can write this as just a normal convolution expression. So all we've done really is scaled the output coordinates in order to make it so that you can use the normal convolution expression. And then we think back to our case I was mentioning before of the electronic black box. So an electronic black box, you can either characterize in terms of an impulse function or in terms of a transfer function, right? So impulse function, you look at a delta function in time and look at what comes out. In terms of a transfer function, you put in a pure frequency and you look at the output that you get from that pure frequency, right? So we can do exactly the same for the optical case. Instead of thinking in terms of a point spread function, which is the same as this, what do we call it? The impulse response. We can think in terms of a transfer function. Now, one thing to be very clear here is, of course, this whole thing, we're talking about coherent systems. So we're working with amplitudes all the time. And so it's the amplitudes that are going to be affected by the optical system. And that's why we have to think of what's called an amplitude transfer function. All right, and we've written that as ATF, amplitude transfer function. So this, if you multiply if you do just a Fourier transform of this convolution, you get a product. And so this is saying that the spectrum out, the spatial frequency content of the image, is equal to the spatial frequency content of the input multiplied by some transfer function, which is the Fourier transform of the point spread function. Right, so this thing here is called our amplitude transfer function. So we have to multiply the spectral content of the object by the transfer function, and then we could do an inverse Fourier transform, and we'd end up now with the image, the amplitude in the image. Does that do something? It wrote something, did it? Yeah, okay, right. So we've already really said it. Okay, so let's look at these examples we said again. So these are two pupil masks that we looked at before. The first one is just a low-pass filter. Lets through the low spatial frequencies, doesn't let through the high spatial frequencies. And this was a phase filter we looked at before, where we only let through the spatial frequencies within this region, but also within that region, we change the phase, the relative phase of the components which are in this region here, right? So this is you can think of this as being the modulus of the filter. This is the phase of the filter, right? So, and outside here, of course, it's 0 anyway, so right, and then this is how we calculate the transfer function from this. This is a distance, right? The pupil is actually a real physical thing, so it's got a physical size. So this is measured in centimetres here. It cuts off at 1.5 centimetres. And in order to convert that into spatial frequency, we have to divide that by lambda f. And this is putting in some figures. That says that you see that u is equal to x double dashed in centimetres times 10 to the minus 3 centimetres to the minus 1. Scaling of our transfer function. And then finally, this is what the ACF is. Is going to be 1.5 times 10 to the 3, which is what this shows here in this diagram. Is identical, just scaled. Of course, to the other example, or any, but the
Professor?
Is going to have this modulus of phase components. Yeah.
Your sound is breaking up a little bit, and I wanted to ask, how is the point spread function related to ATF? Is it just the ATF is the Fourier transform of the point spread function?
They're a Fourier transform pair.
Okay.
Yeah. But you have to be careful with the scalings. Yeah. Okay. So I don't know why the sound, I've moved that a bit closer. Is it?
Maybe clip it on the other side.
I'll clip it on the other side, perhaps. Right, okay, let's see if that's better. Maybe it was flopping around a bit. Right. Okay, so that's that one finished. Where am I going to find something, George?
Yeah, I'll switch. That is proper.
Okay, so now we're up to today. Okay, so really today we're going to carry on talking about the same sort of stuff, I think, is the simplest way to describe it. So what we've been looking at, this is just revising again, with the fact that we're thinking of the 4F system as being a linear shift invariant system. Right, so if you remember, the shift invariance means that the point spread function is independent of position. Right, so there, in that case, you can write the image as a convolution. Yeah.
Let's check the Aperture. None of us thought that is. The first author was dynamics.
Okay. So I hope that this is better. Right. So yeah. So we can think about a 4F system as being a linear shift invariant imaging system, so this is going through then how you calculate that sort of system. So we start off with some illuminating field that comes in here. It illuminates some transparency, and so what you get on the far side of that is going to be the product of illumination and the transparency. right? So this is basically the object of the imaging system. And then it goes through an imaging system with a certain pupil mask, which is related to an amplitude transfer function, which is just a scaled version of that pupil mask. And by doing the Fourier transform of that, you will get the point spread function of the system. So the Fourier transform of the pupil mask gives this point spread function like this. And then your output field is going to be your input field convolved with the point spread function of the system. So notice that so there are two versions of this that are described here. One in terms of x dashed and one in terms of x naught dashed. This x naught dashed one is the rescaled one to make it look like a proper convolution. So we've got rid of the scaling factor f2 over f1, and you see what that does back here in the point spread function is it just changes an f2, 1 over f2 to 1 over f1. So you can work in either of those. Makes no difference really. Okay, so let's now think about how these concepts fit in with what we learned from geometrical optics. And first of all then, we'll look at lateral magnification. What we find then is that if we have a point object here, we just mentioned this before, what it will give is an image which is going to be a blurred image of a point object is going to be this amplitude point spread function. But let's, for the moment, we're trying to find out how this fits in with the geometrical optics limit. Of course, in geometrical optics, there's no diffraction. So you can look at the sort of limiting case as when that point spread function becomes a delta function. So in this case, this is not physical, because you couldn't do this either very easily, but either by, you could do it only by making the wavelength tend to 0, or you could make the aperture tend to infinity, which of course both things you can't really do. But just think of it like this, just to see what's going on. If you could think of the point spread function as being a delta function, the image of our point here would be a point here. And we've already found where that point is. We found that it's a point which is on the opposite side of the axis, and the distance here is scaled relative to this one by the ratio of the focal lengths. And this is exactly what we found from geometrical optics. So the lateral magnification is this m here. mt is the lateral magnification, which is given by minus the ratio of the focal lengths f2 over f1. Okay, so yeah, so if we assume that our amplitude point spread function is just a delta function, then the output amplitude is going to be equal to the input amplitude, but with this scaling. Okay, so that's the result we get. It's exactly the same as you get from geometrical optics. Analysing the same system would also give you this same magnification. Right, now, so this is another example. This is looking at the angular magnification of this system. So before we looked at what happens for a point in the input plane, now we're going to look at what happens to a plane wave at a certain angle in the input plane. And you can see what that plane wave does as it goes through. Of course, the plane wave, when it's Fourier transformed, now becomes a converging wave, which converges on this point. It then spreads again, and then is collimated by this lens to produce another parallel wave there. But you'll notice that the angle of this wave is not the same as the angle of this wave. For a start, you'll notice they've got opposite sign. That one's going up, that one's coming down. But that's what you'd expect, of course, because of this same inversion that we've been talking about. So this input field then is just an exponential phase factor. Okay, so still assuming this ideal geometrical point spread function, the output field is going to be given by this, and you can then express that in terms of thetas, and it comes out to be this. So this is the angle that the angle in was θ1, and the angle out is now minus f1 over f2 times θ1. So again, it's scaled and got an inversion relative to the input angle. So you can see the angular magnification then is given by this expression, minus f1 over f2. And again, that is the same as you get from your geometrical optics. Okay, so based on the interpretation of propagation of spatial frequency, the magnification results are also in agreement with the scaling similarity theorem of Fourier transforms. Right, so you've got an input amplitude, an output amplitude related to an input amplitude, and an output spatial frequency related to an input spatial frequency, and you notice this one's got an f1 over f2, and this one's got an f2 over f1. So this is back to our ideas that if you make the functions smaller, the Fourier transform is broader, and vice versa. Okay, so now this geometry, I guess you could see, maybe I could just draw one. So this is our system. And what I was going to draw, this is F1, 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 F2, F2. And you can see this wave is coming in like this. So we could have drawn an array like this. And this would, of course, been deflected so that refracted so that it's travelling parallel to the axis, and then this would come down like that. So you can see here, this is our θ1. So f θ1 is this distance, and that is also, if you think of this as being theta out, you can see that this distance is the same as this distance, and so f2 times theta out is equal to f1 times theta in. Okay, so everything agrees nicely with geometrical optics, so that's good. So let's look at some examples now. Look at some examples of some apertures. So first of all, the case of, let's put in as our pupil mask a rectangular aperture which has got a distance a and b in the two directions. So we can think of this as being rect x over a times rect of y over b. And we can then work out what the transfer function of that is. The transfer function, we said, is just equal to a scaled version of the pupil mask. So if this is a rectangle, this is also a rectangle. But the scaling has got this lambda f1 coming in. Right, so this is now, of course, it has to have something. This is a function of distance. This is a function of this. Sorry, x is distance, a is distance, right? So this is the dimension is quantity. And in here, this is distance, this is distance, this is distance. So this has to be, of course, inverse distance, doesn't it, to make this whole thing dimensionless. Right, so this is why you need to have something in there to get it to the right dimensions. And then the point spread function is given by the Fourier transform of that. And that's what this looks like. Fourier transform of Rex is sinc. So this is separable, so you just do the two Fourier transforms separately. And you end up with this pattern then that you've seen before. It looks like a central spot and then a lot of extra spots that decrease in amplitude or intensity as you get away from that.
Oh, Colin?
Yeah.
Maybe we should mention that in the notes that I posted, the ATF and PSF were mislabeled.
Ah, yeah. Okay, in the notes that were on the web, this said PSF and this said ATF. But it's pretty obvious when you see them, it's obviously the wrong way around.
And we'll post the corrections.
Yeah, okay, and George will post the correction. Now, I was going to ask one question. This is presumably the intensity of the point spread function that you're plotting here, I suppose.
So it is the square.
The square, yeah, the square of the amplitude point spread function. Right, so that's our first example, very important example. The second one is probably even more important. So this is a circular aperture, and of course most optical systems do have circular apertures, so this is why this is of great importance. It seems to have turned out being a bit like American football for some reason, but never mind. Perhaps it's because it's going over to the US, I suppose.
This would have been okay, except the PSF should look the other way around.
Yeah, that's true, yes. It doesn't know how to do Fourier transforms, obviously. Anyway, this is supposed to be a circle. And if this is the pupil mask, the transfer function, the amplitude transfer function, is just a scaled version of this. So it's again just a circular thing. Sorry, perhaps I just ought to stress this. I mean, it's obvious to you now, I'm sure, by this stage. But so this is plotted here as black and white. Of course, white means 1, black means 0 in this case. So that means if spatial frequencies land on this, those inside this get through and those outside don't get through, right? So this is what we have to multiply our frequency response of our object by in order to get the frequency response of the image. Yeah, so just like before, we have to scale this with these lambda f1s, and then the Fourier transform of this will give the point spread function, and this one has now gone into glorious Technicolor. So this is what we call the airy disk. The equation for this is given in terms of Bessel functions. You've defined this at some point, I presume, but I'm not sure I was here for the lecture, where we defined this jink function, which is basically 2j1 of something over something. So this is our normal airy disk, the image of a point object, which has got this central bright spot, and then a dark ring, and then some bright rings outside of not so bright ring, and then another dark ring, and so on and so on. Right. So and then what we find then is the size of this has got this magic factor 1.22 that comes up all the time in terms of when you look at Rayleigh resolution and things. You always get this magic factor, which is actually 3.83, which is the first 0 of J1, divided by pi, turns out. So that's why you get this magic figure. Okay, and this is just to remind you, of course, when it comes to resolution, we've mentioned before how resolution is related to numerical aperture. So what we're doing here is producing an image of an object, aren't we? So if we've got an object, it's imaged with this lens which has got a certain numerical aperture, right? So this aperture here is what decides the resolution of the image that you will get in this system. This aperture here you see is a ray that's drawn so that it goes to the edge of this pupil mask. If you trace this through, you'll see that it comes back down here. Of course, the numerical aperture is actually equal to the sine of this angle, if you remember. This is, right, so that's what this means. It's not the angle itself. NA is not the angle. NA is equal to n sine alpha, if you remember. The refractive index of the material times the sine of this angle. But what we find is that if F1 and F2 are not equal, this angle here, of course, is not going to be equal to this one. But if the you can see that if NA is small, if NA is small, you can see that these are going to be scaled in the same way as your F1 and your F2. For it to exactly be that, of course, this NA would have to be the tan of that. But a sine, if NA is small, then this distance is the same here and here. So this distance over this distance divided by this distance over this distance is pretty close to being the ratio of the focal lengths. Okay, so we've got a certain NA on the input side, and we've got a certain NA on the output side, and the ratio between those NAs is just equal to the magnification of the system. Right. So actually, of course, we're well used to the fact that light goes, rays of light go equally well in both directions. So we could use this same ray diagram to look at what happens if this was the object and this was the image. But in this case, of course, all these things are now inverted. So if it was producing as it stands here, it's producing a demagnified image going this way. So it will produce a magnified image going this way. So you see that but now the object that you'd have to be imaging is scaled relative to this one. So the resolution will be the same basically in the two directions. I mean, sorry, that's not quite true. What am I trying to say? I'm trying to say that the NA relative to the size of our object that we're imaging here will be the same, whether we think of it as going this way or that way. Of course, in real terms, how small a thing you can actually see with an optical system depends on the numerical aperture of the lens that you're looking at it with, not the lens at the far end. Okay, and then so for our slit aperture, this is what the point spread function looks like, and you can express that then very simply, just replacing our A over F1 by numerical aperture. We've got now that the width of this spot is given by lambda over NA, which is exactly what became about, I guess you said that before somewhere? I think. I don't know. But the resolution of a microscope or whatever, and of an imaging system, you can write in this form. So, of course, this distance will be smallest when this is biggest. So the biggest this could be is if NA was 1 and you make N the refractive index nice and big. And this one actually, these distances are in terms, this is distance in the image in terms of the NA in the output plane, right? So you could have converted this, so this is distance in the object, and then this would become NA in the input plane. And right, and then circular aperture. Our point spread function looks like this, so this is what we get, this delta R dashed here, given by this expression, this 0.61 is half of the 1.22 we had before. But notice this is delta R dashed is the radius of the PSF main lobe. So it's this distance, not the whole distance, it's this distance. Right, so this is why we've got half as, why the 1.22 is divided by 2. Okay, now I did mislead you also by saying from now to the end of the lecture's a breeze, because it isn't, because the next bit is this thing about sampling. So one more bit which is a bit difficult to take in. And this is saying, this is really pointing out about effectively the number of degrees of freedom in an image. So imagine, first of all, you've got an object that you're imaging. So this is this input field. It's got a certain size, which is called here delta x. And of course, in any real practical systems, you don't actually measure it as a continuous function. It's actually going to be measured with a certain pixel size. So here we're calling the pixel size delta x. Right now, so what we've got here then is this function is like an array of spikes in this direction, an array of spikes delta functions in this direction, isn't it? Right. So and the product of those, if you do the Fourier transform of that, you'll get something which is very similar. Again, an array of spikes. If you look in the standard books on Fourier transforms, like Bracewell or whatever, he calls this a comb function, and the Fourier transform of a comb function is another comb function, right? So this is a comb array of delta functions multiplied by a rectangle. And the Fourier transform of a product is the convolution of the Fourier transforms, right? So the Fourier transform of the rect is actually, well, this is really, perhaps I oughtn't to get into that. Well, just think of this then as being in the spatial frequency domain, it's got a certain range of spatial frequencies, and it's made up of certain resolution of frequencies. So what we're going to say is something about Nyquist now. So we can say that we know that in order to image this input field, knowing what this bandwidth is here, we have to sample with a distance. Is that the way? Is that what I'm trying to say? Yeah. The bandwidth is equal to 1 over twice the sampling distance. That's right. Yeah, yeah. And this is in the x direction. This is in the y direction. But we can also, you can see, but the similarity of these diagrams and the fact that Fourier transforms go either way, you can see that there'll be a similar sort of Nyquist type criterion going from the other way round. So that because this has got a finite field, this would mean that you've got a certain frequency resolution there. So there's a relationship between delta U and delta X. The fact that this has got a 2 here, of course, you know from the normal definition of Nyquist, and the fact that this one doesn't have a 2 in, it just comes about from the fact that this is defined here as being 2 times this. Right, so just like before, the spatial frequency domain, those spatial frequencies are then multiplied by the pupil mask to find the spatial frequencies in the image, aren't they? Right, so this is looking now in the plane of the pupil mask. So this is actually the same as equal to this, but just with a rescaling. So these are the expressions for that. So this is just applying that rescaling, putting these lambda f1s in these expressions. So you'll get then how you need to sample in this plane here. Now what you can notice from that is you'll notice that these things are all equal and equal to some constant, therefore. This thing is called the space bandwidth product. So you look at what this means. Delta x over delta x is the field size divided by the pixel size. So it's basically the number of pixels in the field, isn't it, right? So your original object here has got the number of pixels is equal to nx times ny, right? So that's the total amount of the number of pixels, and therefore, well, if you think of it as being a binary thing, it's the amount of information that you've got in that original object. Of course, that information is going to be transferred through the system. So if you look at now the ratio in the next plane, in terms of u's, this distance over this distance is equal to, again, the number of pixels. And as you know, when you do a fast Fourier transform, if you do a fast Fourier transform of something which has got n elements, you get something which is n elements. So it all works right. So effectively, you can think of this as being a bit like, of course, you can't really, if this is actually got some finite bandwidth, then of course you can't sample on points. So it's a bit of an idealization to think in this sort of terms, really. But nevertheless, it gives you a good idea. So, of course, for a repetitive type function like this, also, you can think in terms of a Fourier series becomes a Fourier transform, right? So all we're doing here is really resolving our function here into a Fourier series. And the Fourier series consists of a lot of sine terms, doesn't it? Sine of n, sine of n, and sine of x, and sine of 2x, and so on and so on. And these correspond in the Fourier domain to these points on this grid, right? So each of these points represents the particular Fourier series component in the original object, if you think of it like that, right? So an idea of a space bandwidth product is quite a powerful way of thinking about the fundamental limits of an optical system. And people have gone on to study this sort of approach in much more detail, actually trying to get around the limitations that I just described. The fact that, of course, we've truncated this means that this is no longer a repetitive function. And similarly for here, right? So actually, this idea of thinking of truncated repetitive functions is a bit of an anomaly, really. But people have come up with mathematical ways of dealing with these sorts of systems, which are probably way beyond what we're going to get to in this course. Okay. Did something come up then? Oh, yeah. Next slide. Okay. This is just pointing out then, we said that you put a mask in here, and that mask produces a certain transfer function, amplitude transfer function, and the Fourier transform of that gives the pupil function. And we've shown a couple of examples of what this pupil function looks like and what the image would look like. But this is just pointing out that actually, of course, that means that we can choose whatever we want to put in there in order to produce the results we want. So this is what George has called here pupil engineering, which Ernst Stelzer doesn't believe in, I think, from what we were saying. But anyway, so the idea is that by changing this mask, you can improve the properties of that point spread function in some way, which would suit the particular application you're looking at. Actually, it turns out that you can't actually do a lot better normally than the very simple example of a circular aperture. You know, there's the circular aperture is actually very special because it does give, according to some measures anyway, a very sharp point spread function. If you can come up with other pupil functions that make the central lobe narrower, but normally what happens is then the size of the side lobes gets stronger. So it's a sort of compromise. You can't have a very small central lobe together with very weak side lobes. Okay, so some examples then. Let's imagine first of all our object is our intensity at the input plane is this rectangle with this stripy pattern. So we're going to then look at what happens if we image that with some mask that we put in here. And what should we put in there then? Well, the first one, let's put in something that like this. So now this is going to let through, this is a low-pass filter, isn't it? Right, so it's a very small low-pass filter as well. So it only lets through the very slowly varying parts of that object, but it stops all the fast variations of the object. Right, so if you look at the object, you'll see that it's got this stripy pattern, which is actually a very fine structure. Right, so these have actually really been calculated using MATLAB, not by me, by George. And so this is what you'd see in the output plane of that. So there you are. You can see that this stripy pattern has disappeared virtually. We've lost some sharpness at the edge, though, because we've also lost the high spatial frequencies, of course, that define the edge. And a sharp cutoff at the edge will include quite a lot of high spatial frequencies. But anyway, so that's a good example of spatial filtering. Then the next ones, we're going to look at something which has got a bit more structure. So this is MIT written as a binary mask. So this is our original object. And we're going to image that in an optical system and look at what the image looks like in different cases. So the first one is quite straightforward. We've got now a circular aperture. So this is what the image looks like in this case. You see that there's already a bit of artifacts in that image. It's no longer, you can still read it as MIT, but you see that inside the letters, you'll see there's some structure there which is not really present. So this is some sort of edge ringing, I guess, from the fact that this aperture has got this sharp cutoff at some particular spatial frequency. So if you made it so that it tailed off gradually, you could probably get rid of some of that those fringes there. But okay, so that's an aperture. So we've got rid of some high spatial frequencies. Let's look at what happens if we reduce the spatial frequencies even more. So this is making the aperture smaller, and now you can see that the resolution has degraded. It looks rather blurry now. You can't really see whether it says MIT or HIT or maybe HIY. It's all getting a bit vague, isn't it? You can see that it gets a bit sort of blurry around the edges. Yeah. So if we make that,
Colin,
yeah.
One more thing to point out here, which is kind of obvious, but it's worth pointing, is that if you do this, also the average brightness of the image would decrease as you stop down the aperture, But in this case, they cheated. They normalized the intensity to the full level, so it is visible in the projector. But in a real system, it would also become less bright.
Right, okay, yeah, so I didn't notice that because I didn't do the calculation.
Yeah.
But yeah, okay, so, all right, so of course if this aperture gets smaller and smaller, the amount of light going through gets smaller and smaller. And so in the end, you'd end up with black. Right, so anyway, we're now going to make this even smaller. What would you expect? Well, you'd expect, again, the thing to become more blurry looking. And in fact, it really does become, just before we carry on, just take this fully in, you'll notice that there are 4 legs here, 4 straight lines. And these two are closer together than these other spacings, right? So as we decrease the size of the pupil, now you see what's happened. This is quite amazing. I was quite surprised at this. The 4 legs have become 3 legs. So I guess these 2 central legs are now not resolved. They're below the resolution limit. And you'd have no idea, of course, what that said now. It looks something really blurred. So we're not getting enough information, obviously, there to be able to be able to see the image properly. Okay, then let's try doing some other funny things. So this one is a high-pass filter. Now, so what we're doing here is we're blocking out this central part and letting through all the other filters, all the other frequencies. Now, there's one other thing that we ought to mention here, is that this, of course, is done, these calculations are done using FFTs, right? So we're actually working on a field of a certain size when we calculate the FFT. So the fact that this, as you know, FFTs that do like a sort of repeating, don't they? Right? So this is not really quite the same as this going out to infinity in spatial frequencies. So I think that the result in the image you might get could depend a little on the properties of the zero padding and things like that in this case. But anyway, this is the image in this case. So you'll notice that we've got the high spatial frequencies. So we actually get some sort of enhancement of the edges. You see the edges come out really very crisply now. So you get this enhancement of the edges. It's like an edge enhancement filter. But on top of that, there's some rather strange sort of glowing patterns, which I'm not really quite sure what they refer to at all. But you could, I guess, think of them as being some sort of artifact. It looks a lot better on this screen than that one, actually, interestingly. So if we do another of these high-pass filtering, but with the central block even bigger, this effect of edge enhancement shows really nicely now. So all we're now seeing is the edges, and the bits inside the letters are not showing up, or outside the letters. So neither. Can't remember what the object looked like now. Yeah, it's interesting. The object, whether it was black writing on a white background or white writing on a black background, probably this would look very similar. It wouldn't make a lot of difference, I don't think. Okay, and so all these examples have been circularly symmetric type patterns, but you can also, of course, put in things which are not circularly symmetric. So this is throwing out these frequencies here and here. So we haven't done anything here, so we're going to have a high resolution in that direction, but in this direction here, we've reduced the resolution, so we'd expect it to be blurred in the vertical direction. And of course, just to prove that, we can do the opposite, and this one now is going to be blurred in the horizontal direction. So you see here, again, you're almost losing the resolution of those 4 legs. Okay, and then probably one of the most important applications of pupil filters is in phase imaging. So this leads on to Zernica phase contrast, which Zernica got the Nobel Prize for. It's quite interesting. It was a long time after he invented it, though, I believe. He invented it sometime in the 30s, and it was commercialized by, actually, he seemed to have managed to get Zeiss and Leica and everyone to make it. So he must have sold his patent to lots of people. But anyway, eventually it became very popular, but it didn't get the Nobel Prize until the 50s sometime. Very useful for a long time. I think eventually it got, to a certain degree anyway, outclassed by some later techniques, but still used a fair bit in the lab. It has one advantage of being quite cheap as well. Anyway, what you're trying to do with phase contrast is image a phase object, and this is an example of what a phase object might look like. Imagine, for example, you've got some glass slide. Well, one thing which would approximate quite well to this is if you had a biological cell sitting on top of a glass slide, right? So this shows something like that. But actually what we're thinking, well, if it was a cell, of course, the refractive index of this would be slightly different from this. But that's really not an important difference. So this is looking on the top of it. So here we've got this object, which has got a certain thickness. And what we'd like to be able to do is to produce an image which actually shows up the shape of this object, right? Which might be a cell or something. So this phase object, we can think of the light propagating through this and producing a phase shift then. So the phase shift is given by this expression. So n here is the refractive index of this cell. We have to have n minus 1, of course, because the cell is displacing air. So if the cell wasn't there, there would be air there. So we have to subtract away the air that would have been there. So the phase is 2 pi times n minus 1 times the thickness, which is a function of x, or of x and y in this case, divided by the wavelength. And so if we illuminate this with some certain illumination field, then what we'll get on the output side is just this times this. There's no, e to the I phi, our object just behaves here as a pure phase object. There's no modulus change, only a phase change. Yeah, so useful for imaging biological objects such as cells, but not only that, it's got applications in material science and so on. Yeah, so if we looked at the, imagine this, this illumination is just unity, and we look at the modulus squared of this object function. You see, because it's just only a phase object, when you look at the modulus square, you'll see nothing at all. So if you looked at this in an ordinary microscope, you wouldn't see anything. You'd just see completely uniformly white. So you wouldn't see the shape of this thing that we're trying to see. So the question is, how can we go about that? What can we do to solve that? What we're now going to look at is back to this MIT pattern, and we're going to think of an MIT pattern which is now not a binary object, but a phase object. So imagine that this is our object. So this represents phase. So red represents a phase change of 0.1 of a radian. And this one shows the modulus of this object, which we're assuming is completely uniform. It's a pure phase object. And if we looked at this in our ordinary optical imaging system, all we'd see is the modular square of this thing. So we'd see basically nothing. So the question is, what can we do to try and improve that? Well, Zernicke came up with the answer. Actually, this is not quite the way he does it. We're not going to really do the way he does it, but the principle is here anyway. What you do is you introduce a pupil mask, which has also got a phase object in it. It's got basically a small region at the center, i.e. where the low spatial frequencies are, which we change the relative phase of those spectral components relative to the other spatial frequencies by pi over 2. So we put that in our system. And what we find, as it says there, is we could actually, we get contrast of the phase. We actually see the phase now. And this will explain why that works. So this is what we're doing. We're putting in our phase MIT thing here. And we're putting in this pi over 2 phase mask here. So that's what it looks like. It's some bit of dielectric which has got this central region which changes the phase by pi over 2. Ideally, what we want to do, as it says here, is for this to be very small. What we're trying to do is to use it to change the phase of just the DC component, the unscattered light component relative to all the rest. But of course you can never do that because it's got to have some definite real size. So it's obviously going to, whatever size it is, there might be some low spatial frequencies of the object which are going to be, the phase is going to be changed in the same way as the DC term. So let's look at the maths of how that works. So what we do is we assume our phase object is what we call a weak phase object. It's got the form e to the I phi, but we think of that as being approximately 1 plus I phi, and we neglect all the other higher order terms in the power series expansion for the exponential. And you can see then that in an ordinary system, what we'd see is, you can think of it, we said, keeping all the terms, the modular square of this is obviously 1. And this also, the modular square of this to the first order of small quantities is also going to be 1. Of course, if you square this, you'll get phi squared terms. But actually, there are also really some extra phi squared terms in this series, which actually, if you do it properly, all cancel out. So you still must get 1. Right, so, okay, so what we're now going to say, this is our object, but now this object is going to go through this mask here, which is going to change the relative phase of this relative to this. So if we change the 1 to I, we're now going to get I plus I phi. And therefore now the output that we get is going to be given by, where's that? This should be intensity out, should it? Yes. Yeah. The intensity that you see is the modular square of this, which is 1 plus phi squared, which to small, because phi is small, we can expand that to first 2 terms of the series, and we get 1 plus 2 phi. Right, so now we're getting an image where the phase is visible to the order of this order of the weak phase object phi. In this case here, we weren't seeing anything to the order of phi. The lowest things that were there would be of the order of phi squared, which is going to be negligible if phi is going to be small enough. Right, so there we are. So by putting this in, we've managed to make this phase object visible. So this is the demonstration of that. So this is our looking at our phase MIT, and this is the size of our phase mask. So it's quite big here, actually. So I guess it's changing the phase of the central, the DC term, but it's also changing the phase of some low spatial frequency terms of the MIT, which I guess accounts for some sort of imperfections in this image. And I think a lot of the ripples, again, are coming from the fact that this has got a sharp edge to it. Probably if you smooth this, you could make it so that you didn't get such strong ringing in this thing here. But this is the next example. We've now made this a lot smaller, so it's now changing the phase of the DC term, but it seems that the object itself probably has got very weak components in that region, and you end up then with this really wonderful image. So I guess that really shows the power of the Zernica phase contrast method. That's the end. How are we going? Good, we're up to time. I've been fast. Right, any questions anywhere? Anyone want to look at these nice pictures again?
I've got a question, actually.
Yes, good. Yeah.
It seemed like in the last analysis that you're doing, phi was much, much less than 1, but then you were saying that phi was pi over 2.
No, two different phis.
Okay.
How do I get back in this?
Oh. You click the play button.
The play button. Ah, play button, got it. Yeah, okay. Yeah, so two different phis. The object is the one that has to be weak. So here we said the object has got this phi, which is e to the I. So we've got e to the I phi as the object, and this phi has to be small. Somewhere it said, maybe it was after. The phase MIT object, here we are. The phase of MIT object, the phase change is 0.1 of a radian. So 0.1 of a radian we're taking as being small. So red here represents 0.1 of a radian. Red there doesn't represent 0.1 of a radian. So this is our mask. So this has got a phase change of pi by 2. So which is much bigger than 0.1 of a radian. Okay? Yeah, so it's the object that has to be a weak phase object, not the mask.
I think the principle still works for strong phase objects, but the explanation is easier if you assume a weak phase object.
Yeah. I think I agree with that. Yeah. But actually, for a strong phase object, you do also get an image in an ordinary imaging system.
Right.
But it's very complicated to actually relate it to the object. It's a bit like frequency modulation.
Or another example of a strong phase object is the waves in a swimming pool. They create an image at the bottom which looks like very bright lines. In a way, these lines are an image of the, index of refraction of the water. And these lines are known as caustics, but it is very difficult to interpret them and relate them to the actual shape of the water.
Yeah. Okay, yeah. Any more questions? Not many from this end today either. I usually rely on Shalin to come up with some questions. You know, at FOM, he was in FOM, and he asked the very first question of the whole conference.
Oh, that's quite a distinction. To the plenary speaker, I imagine.
Yeah, to the plenary speaker. All very clear? I think, I think these demonstrations are really great because I think that you get a very nice feel for what happens.
We have the quiz coming up, but we have enough time. Maybe we can introduce temporal coherence at the beginning of the next lecture, or should we just stop here?
Up to you.
Anybody has no questions at all? We have a quiz coming up. This is your chance to ask questions, I suppose.
So when's the quiz?
On Monday.
Oh, right, okay.
That's why he could not answer a question. He was expecting a phone call.
Yeah.
When you have a phase grading, normally you try to solve for a system that has the 4F system. You normally play different tricks. One of them is you try to expand part of the grading in a Fourier series, and after that you somehow manage to decompose that into something easy. Or you actually change the e to the exponent to something easier to handle in terms of you look at the phase and you look at it, and if it is like pi over 2 or it's pi, you change it to something different that is easier to handle. Any advices on how to solve those? I found those particularly tricky to actually get a grasp of how to solve the things.
Not quite sure what you're saying. I mean, if you've got, I mean, you start off by saying you've got some sort of grating object, and then if you illuminate this, you'll get a series of diffraction orders. And of course, you know, the relative strength of these might be complex to account for the phase changes. So what you're saying is that by changing the phase or whatever of these components, you can improve the image. But is that what you're saying? Something like that?
Yeah, my question was more in the order of like how to handle the math. Normally,
yeah,
if you get something in terms of Fourier series, you get a bunch of terms.
Yeah.
And it's kind of like it ends up being pretty messy.
Yeah, but you know, this is then going through the mask. So if we've got some mask which has got some phase variation, so the relative strength of these grating orders will just be changed by the phase of the phase mask. So so the forward problem, I got the feeling that maybe you were trying to solve the inverse problem. You know, what do you, if you know what the image looks like, how do you know how to improve the image or something like that? But normally, of course, if you knew what the object was, then there probably wouldn't be a lot of point imaging it. But anyway, to calculate this is all you have to do. Just multiply the strength of these grating components by the strength of your mask, both in amplitude and phase. So it's very straightforward, really.
Yeah. And I don't think there's a way out of the Fourier series expansion. Like, if you really want to solve this kind of a problem with a phase grating, you must compute the Fourier series expansion of the grating. Unless you, for example, if the phase is weak, then you can simplify it, as we just saw in the example. But otherwise, yeah, you have to go through the pain of the Fourier series expansion.
Okay, thanks.
But, yeah. But, you know, there are sometimes, of course, for lots of other objects, you can just look them up in the tables of Fourier transforms. And even the Fourier series, you know, you can sometimes get from that, of course. I mean, for example, you know, these square wave gratings like this, you can think of this as being this convolved with this. So the Fourier transform of this is going to be the Fourier transform of this, which is a sinc, times the Fourier transform of this, which is another one of these, right? So So you end up with basically an envelope which is this, and then some components within here, and the height of these gives you the strengths of these different grating components. So I think there was a sketch like that in one of the earlier slides showing how you can think of that. So these are the strengths of the Fourier series for this object. They're just given by the product of a sink and an appropriately scaled sampling function.
I think you need to push the paper a little bit up.
Oh, sorry. Yeah. Can I do that? Oh, yeah. Okay. Sorry. There you can see what I was saying. Yeah. So sometimes you can find shortcuts to be able to deal with some of these Fourier series without having to go through the hard work of doing what you did when you were a first-year student.
There was a homework like that actually, where it was not quite phrased like this, but yeah, I had you guys compute the Fourier series in this clever way.
Okay, no more questions? Yes, Shillin's got one. Yeah.
What is the, how did the idea of numerical aperture come about, and why is it defined as a sine of an angle? What, is there a rationale?
Tangent of an angle? Yeah, good
Yeah.
point.
Yeah.
Well, I guess it's because George, in one of the earlier lectures, pointed out that according to Snell's law, you've got that n sine alpha is an invariant. So as rays go through a series of interfaces, then that will be an invariant. It won't change. So I think that was the justification for it. Yeah. But yeah, you've hit something which is quite, the fact that sine theta isn't tan theta is basically why paraxial optics eventually breaks down. And so a lot of the stuff that we've presented has been based on assuming that these angles are all small. And a lot of these things just fail if you can't assume that theta angles are small.
For example, aberrations are another type of not shift invariant behavior, right? If you get into, with the exception of spherical, but all the other aberrations are not shift invariant, so our approximations failed. For example, astigmatism, if you recall, astigmatism occurs if you have a plane wave entering a lens at, I'm sorry, I should have said comma. Comma occurs if you have a plane wave entering a lens at an angle. So of course, as you increase the angle, the comma becomes worse. So that is a shift variant.
Okay, do you want to stop, or do you want to say something for a few minutes?
We could talk about the Talbot effect.
Oh,
that
yeah,
we skipped in the previous lecture.
Yeah. Shall
I can have to find it.
I think they'll be interested in that, because I don't think my students have ever come across the Talbot effect before. Except I think we did mention something. Was it with you? Maybe you had a chat. No, not this time. He was a very long time ago. I was just going to say. I'll come and say it there. All right, I'll come and say it here. I was just going to say that this Talbot effect, he was actually a very long time ago. I can't quite remember the history, but it's a very old effect.
And I think Talbot was also another professor of mechanics who ended up doing contribution in optics, if I'm not mistaken. Very similar to Maxwell and a bunch of other people. No. I went the other way around. I shouldn't be expected to make a contribution in mechanics, not enough. Okay. Oh, I'm not showing anything. Sorry. So the Talbot effect is it is a phenomenon that happens when you have a periodic pattern, for example, a gradient, and you illuminate it with a plane wave. And then what you do is you observe the intensity pattern forming after the field diffracts, after it has gone through the transparency. So I don't know how well the movie will show, possibly because of sampling of the projector, it might not show. But if you look carefully, you will see that as the field diffracts, the original grating pattern becomes visible at certain distances, then it disappears, then it becomes visible again. I will play it in the case of the diagonal grating, and then I'll play both of them again. So as you can see, it diffracts, then the sinusoid reappears, and so on. In this case, it is actually very clear when it will stop happening, because as we said, in the case of a grating, the field after the grating splits up into diffraction orders. Now this grating is finite, so as you can see, the diffracted orders separate, and by the time it reached here, you can see that you have basically 3 rectangles that have split up out of the grating. So the Talbot effect will stop happening when the rectangles completely separate. It hasn't quite stopped yet, but it can only happen in the region of overlap between gratings. Okay, so the next, let me play this once again so you can see it. So again, look out for the repetition of the periodicity of this pattern. Now, and again for the next one. I hope it is showing up also in Boston. Here we can see it very clearly on the projector. Okay, so yes? Okay, so the next slide is cross sections.
George?
Yes.
Did you say that this effect occurs only where there is an overlap between the diffraction orders of the...
Yeah. So if the grating is infinite, then of course it occurs forever. But if the grating is finite, eventually the orders will separate, and then it doesn't happen anymore. So this is cross sections of the intensity pattern at different distances, which of course I chose strategically because I know the formula that this effect follows. Of course, you don't know the formula yet, but anyway, this is what you see. Now, what is really interesting, and you may not have seen in the previous one, that there's also a plane where you see a periodic pattern at twice the frequency. So this is like the second harmonic of the original grating. So the question is, why does that happen? Well, there's a physical explanation, which is probably the most interesting, and that has to do with the following. So this really goes to the heart of diffraction, why really diffraction happens and why we see all these phenomena. So imagine that you have a plane wave going into a sinusoidal amplitude grating, and of course in this case we only get 3 diffraction orders as we discussed, the +1, the -1, and the DC. And these diffraction orders, each one of them is really a plane wave. So you have now, you started with 1 coming in, but after the grating you have 3 plane waves propagating out. And imagine that you pick any point on the grating, really, it doesn't matter, but let's pick this one, and we draw a sphere of a radius z. We draw a sphere centered at this point. Now, if you compare the 3 plane waves and you take the plane waves originate, well, you take arrays, really, centered at the center of the sphere, and if you compare what happens to these plane waves by the time they reach the shell of the sphere, then you realize that they all have the phase delay, the same phase delay, because they all propagated the same distance from the center to the edge of the sphere. They all propagated by the same amount, so they have the same phase delay. However, when we observe the field in all of these cross sections that I showed before in my movie and in the calculation, I did not really observe the field on a sphere. I observed it on a plane. So if I center this plane at a distance z from the axis, then the central order that propagates on axis, it sustains a certain phase delay, but you can see that the +1 and -1 orders, they propagate a longer distance from the sphere to that grating. And you can calculate this distance. It is the difference between z itself and an expression that you get from Pythagoras' theorem, right? So this expression is basically the hypotenuse of this triangle all the way out to the plane. And if you do also the paraxial approximation, then you find that it's given by quadratic. This is our familiar quadratic term that appears in the Fresnel kernel and in all of these expressions of Fresnel diffraction. So however, now what am I really observing? Well, in this plane, I observe the interference pattern. You can think of it as a Fresnel diffraction pattern from the grating, or you can also think of it as the interference pattern between these three plane waves. So it's like an interferometer, right? I mean, physically, as I think Professor Sheppard mentioned, and I also mentioned at some point or another, diffraction is really no different than interference. It's just that in the case of diffraction, you have many, many, many waves interfering produced by the Huygens wavelets originating at your original object. But in this case, instead of thinking of all these Huygens wavelets, I'm better off just thinking about it as plane waves interfering, because the physics of the grating tell me that the diffracted field is really composed of three plane waves. Okay, so now there's a phase delay between this guy and this guy. Actually, this guy and this guy, the +1 and -1, are always in phase, but they can have a difference in phase delay between themselves and the 0th order. And of course, if that phase delay happens to be 2 pi, then there's no phase delay. And when did these things start as having no phase delay? Well, at the grating, right? So if I let this thing propagate enough, what is the parameter I can vary here is z. If I let z grow so that this phase delay becomes equal to 2 pi, then I reproduce my original grating, because of course there was no phase delay here. So when the phase delay becomes 2 pi, then again I will see the same pattern. It is not as obvious why you get it is not obvious why you get a subharmonic, why you get the second harmonic that I discussed before, but it's a little bit fortunate that the lectures got shuffled in order, because by now you remember from one of the examples that Professor Sheppard showed, when you actually get rid of the DC component, you can get a second harmonic to pop out all of a sudden. A very similar thing happens if you get a pi phase shift. This pi phase shift can produce a very distinct subharmonic. So this is the reason. Okay. Now the rest, I will not go through, but there's a mathematical, well, I can go through very quickly, I guess. There's a mathematical way to derive it, and it is also described in Goodman, and I also did it in the slides. So if you start with a field after the grating, of course you can express it as the diffraction orders. We did this before. You can Fourier transform the field after the grating. We did this before also in the context of the 4F system, but mathematically it is really the same. Each one of these exponentials in the field will produce a delta function. Now the question is, what happens after the field propagates by a certain distance? So in order to do that, let me show the Fresnel diffraction again. This we're familiar with. We said many times that Fresnel diffraction is expressed as a convolution that has to do with the Huygens wavelets propagating and producing spherical waves that again interfere. So the interference is expressed as a convolution integral. But because of the properties of the Fourier transform, if I take Fourier transform of the output field, then it will be expressed as a product of the Fourier transform of the input field times the Fourier transform of this Fresnel kernel. And I really am not going to prove this, but you can look up in Goodman's book, in the table of Fourier integrals, you can look up the Fourier transform of an expression like this one, and you find that it looks very similar. This is a quadratic phase delay. Its Fourier transform, it also looks like a quadratic phase delay, but it has two key differences. One is that it has a minus sign, so it is actually a quadratic phase advance, if you wish. And the second is, of course, the scaling theorem that will take up this factor of lambda z from the denominator and we'll pop it up in the numerator. And of course, the happy outcome of this scaling operation is that also the units are preserved. This quantity has to be dimensionless, so indeed it is. I have distance square in the numerator as well as the denominator. In this case, u is a special frequency, so it is inverse distance square. By multiplying by this distance square, I get again a non-dimensional quantity. So the scalar theorem works quite nicely. And you can also think then of, we talked about transfer functions in the context of the 4F system, but really you can also think of a transfer function in the case of Fresnel propagation, because it is shift invariant. Clearly, if you have free space, that is truly a shift invariant system. No matter where you start in free space, you would expect the field to shift by the same amount, though it would be really odd if anything else happened, unless you believe in space anisotropy, I guess. Only close to the Big Bang, this, this property was not observed. But since billions of years have lapsed since the Big Bang, space is isotropic, so we don't have to worry about it. So of course, the Fourier integral approaches, and of course, then this quantity that we derived is simply the transfer function of free space. It is another quadratic phase delay. Okay, so we can actually apply this formulation now to the mathematics of the Talbot effect. All I have to do is multiply the Fourier transform of the grating itself. All I have to do is multiply it with the Fourier transform of the Fresnel propagation kernel that is another quadratic phase delay. And this multiplication is very easy to do because I'm multiplying a function that I know with a bunch of delta functions. So all that will remain really is the value of this quadratic phase delay computed at the spots where the delta functions occurred. And this is what I do in the next slide. This looks a little bit nasty, but really that's all you need to know. It looks like an expression very similar to the grating. This is the DC component, this is the +1 diffracted order, this is the -1 diffracted order, but it picked up this additional quadratic phase delays, which is really, it came out of the math now. I used Fourier transforms and convolutions and everything else. But if you go back to my picture here with the sphere and the phase delays, you can really see that this is really the same expression. It came out of the math in one case. It really came out of a physical picture of phase delay of planes where they propagate, but it's all consistent. It is really all the same answer. And after a little bit of more pain, which involves really taking one more Fourier transform and then combining these things to form a sinusoid, you get this expression for the field. And now you can see what I was saying before. This looks like a nasty phase delay that got appended to the diffracted field. This is really the diffracted field now. So this is the Fresnel diffraction pattern from a grating. But if this quantity in the exponent happens to be 2 pi, then it is not there anymore. So you recover your original grating. And okay, that's the intensity. And you can also see from this, you can also get the condition for the second harmonic generation. Basically, if you kill this term, which means that this quantity becomes pi over 2, then this disappears. All you're left is the cosine square, which is, of course, the second harmonic. So this is so these are really delineated in the next slide. If the propagation distance, if this quantity, this is also non-dimensional, it is distance square over distance square. If you propagate far enough so that this equals an even integer, then you get a replica of the original grating. This is basically, this quantity becomes a phase delay of 2 pi.
If you get it to become equal to an, oh yeah, and you call it this distance a Talbot plane. If you get it to propagate so that it is an odd integer, then it is pi that shifts this term by pi. Basically, you flip the sign. Now the grating has shifted. If you really work it out, you still get the same sinusoid, but shifted by half a period. And finally, if you completely eliminate the linear term by choosing the distance to be pi over 2 or 3 pi over 2 or 5 pi over 2 and so on and so forth, then you can actually get, somehow I forgot to close my bracket here, but anyway, then you get a period doubling and you get a second harmonic. Okay, and this is the schematic. These are basically now repeating periodically every time you add this propagation distance. I'm sorry. Jesus, these are flipped here. This would have been lambda, 2 lambda z over lambda square, 2 lambda z over lambda square. So basically every time you propagate by this quantity, you go from a Talbot subplane where you have a second harmonic to a half period shift to another second harmonic to a replica, and then it repeats. So these are the Talbot planes. Now we're out of time, so I will say something that's interesting for those of you who have time to stay. This, as Professor Sheppard mentioned, is a has been noticed since a very long time ago, but more recently it became actually a kind of a hot topic of research because people noticed that it happens not only in sinusoidal gratings, but it can also happen in every periodic pattern. If, for example, if you have a square grating, it would also have its own Talbot planes. And then not only that, but people notice that it can happen in some strange patterns that are called quasi-crystals. So I don't know how many of you have taken solid-state physics, but in solid-state physics they teach you that there are certain patterns in nature that, how do I want to say this? There are certain symmetries in nature. And for example, a very simple symmetry is rectangular symmetry. If you take this as a unit cell and then you repeat it, you can keep filling out a space like this periodically. Another example is a hexagon. Let's see if I know how to do the hexagon. Okay, I ended up doing an octagon. Sorry about that. Okay, that's a pentagon. I need one more, and okay, I got my hexagon. Okay, that's nice, because this indeed does repeat. Okay. Never mind, anyway. Okay. Okay, that will repeat. Okay, good. Okay. Okay, so fortunately I did the pentagon also. So the question is, what will happen if you start sticking pentagons next to each other? Now this will be really impossible for me to do, but you can imagine if you try to stick another pentagon, identical pentagon next to here, then you will get something like this, I guess. And then you can keep doing it. But you noticed when I did it, then I got to stick a pentagon, but it is slightly rotated. Okay, it's really difficult for me to draw, but if you Google quasi-crystals, I don't know if it's the first website that comes up. There's a website at Caltech. In the physics department at Caltech, you will see some very nice pictures of what happens if you stick pentagons next to each other. That's called a quasi-crystal. Okay, now why are people interested in this? Physicists are interested because in solid state they teach you that if you have atoms arranged in one of the patterns that produce symmetries, then if you pass X-rays through this symmetric lattice, you get a diffraction pattern. Very similar to a grating that we saw here, except that would be in 3D, because the symmetries are very simple in 2D. I think in 2D you only get two, right? You get the rectangular and the hexagonal symmetry. In 3D you get many more symmetries. I forget how many do you get. I think it is 7 groups or 12 or anyway. I should refresh my solid state physics, but anyway. And each one of these gives rise to, each symmetry gives rise to a distinct diffraction pattern, and then crystallographers, basically by passing X-rays through a crystal and observing the diffraction pattern, they can guess what was the original symmetry that produced it. We also know that non-symmetric patterns can produce diffraction, and that is what won Crick and Watson the Nobel Prize, because they figured out that if you have a helix which is not quite symmetric, it can still produce a diffraction pattern, and Crick was a very clever mathematician. He solved it, and he won the Nobel Prize for it. Anyway, recently people observed that quasi-crystals like this one, if you take pentagons and you stick them next to each other, they also produce a diffraction pattern, which looks actually like a bunch of bright dots in a pentagonal kind of symmetry. It looks very funky. If you go to this Caltech website, you will see it. And then people also noticed that this kind of thing also produces Talbot patterns. If you diffract a field from a pentagonal quasi-crystal, it will produce Talbot patterns as you go behind it. And that caused quite a bit of stir. Actually, there's a lot of papers analyzing this and looking into interesting. So anyway, I don't know if this has any use. It's kind of interesting physics, but yeah, people spend some time on that. Oh yeah. Actually, Talbot effect found use recently in a very surprising way in lithography. It is a very easy way to reproduce a pattern lenslessly, as long as the pattern is periodic. And so for a planar lithography is not very interesting, but nowadays many people want to make photonic crystals which are periodic. So in a photonic crystal, you want to start with a volume, so this is a cross-section, and you want to write patterns that looks like this. So for example, what you do is you take a polymer, okay, I take it back. You take a monomer and you expose, if you could expose somehow these regions, and then you develop it, then you would end up with a structure that has low index in the unexposed regions and high index in the exposed regions. That is a photonic crystal. So the question is, how can you do this? Well, one way is with the Talbot effect, because the Talbot effect will actually focus the light very sharply in the Talbot planes, and then you get your exposure, but everywhere else the light is kind of diffuse, so it does not expose very much. So if you play with the threshold of the photoresist, you can actually get a pattern to work like this. So there's a colleague of mine at MIT, Ned Thomas. I don't know if any of Ned's students are in the class, but he came up with a very clever system that he can expose and create photonic crystals this way. And then, interestingly, a student of mine discovered that if you vary the duty cycle of this thing, I may be disclosing, everybody here is MIT, right? And those of you who are NUS are sort of, okay, bound by a vow of secrecy or whatever. But anyway, I may be disclosing something that we have a patent pending for. But anyway, so it is also well known, people have analyzed patterns with a duty cycle that is different than 0.5. So for example, if you have a gradient that is like this, this also produces a Talbot effect. So it will also produce replicas of that pattern. So, but my student discovered that if you vary the duty cycle, that's really interesting. And we don't fully understand why, but it is true. I mean, it is physically correct. We don't know how to explain it very intuitively. But mathematically, you find that you have a pattern with a fixed period, but a variable duty cycle, for example, like this, it also produces a Talbot effect. Not forever, but over a finite region, maybe about I don't know, it depends, but maybe about 10 or so Talbot planes, it reproduces itself. So it is also possible to make non-periodic patterns, which, as Colin knows, we're very interested in making non-periodic kind of, they're not photonic crystals anymore, but they're non-periodic strong index modulations. That is possibly one way to do it. So,
George, it seems like
surprise effect, yeah.
it seems like that was still a periodic pattern, though.
Oh no, because the duty cycle varies. To call it periodic, it must have the same duty cycle in every period.
So even though it repeats every period with a different duty cycle, that's not periodic?
Of course not. Would you call this function periodic?
I understand what you mean about the duty cycle changing, but it's got a definite period to it where features are...
Yeah. Yeah, but it's not periodic. Okay, what you're saying is a possible explanation for why it has a Talbot effect. It has a Talbot effect because it has this fundamental period underlying the variable duty cycle.
Right, I look at the duty cycle as changing the orders that are coming out for that particular region.
Well, in a slowly varying approximation, perhaps, yeah. I mean, this thing, I have not looked at the diffraction pattern of this thing in detail, but yes, it would produce diffracted orders, but it is not clear how you would compute their strength from a Fourier series. At least I don't know how to do it. There may be a way with some adiabatic approximation. Because it is true that in our simulation, the duty cycle was very slowly varying. And I believe it is also true. In fact, I think Will, my student who did this, he also did the simulation with a fast varying duty cycle, and he found out that the Talbot effect actually does not happen if the duty cycle varies fast. So yeah, there's certainly an adiabatic approximation happening here. But yeah, I guess we haven't really worked out all the details, but it is sort of interesting still. Anyway, yeah. It's one of these things that the reason I'm bringing it up is because, yeah, the Talbot effect doesn't look like something particularly useful. It looks more like a curiosity. But yeah, I guess sometimes even curiosities can find applications, right? So.